This is the final part of my lecture on parametric tests for comparing means, in which I'll give a summary of what we've seen in the whole of the lecture. First of all, let me just say something about the power of these tests. If you remember from our lecture on hypothesis testing, the power of the test is the ability to detect an effect if it's there. So we're looking for a good power, and a power calculation should ideally be done before you start your research to know that it's going to yield a possibility of giving a sensible result. Power calculations can be quite complicated, but there are several online tools available to help. For example, at DSS Research, you can do a power calculation for a z-test, either one tail or two tail. One sample, you select what they call averages one sample, and for two sample, averages two sample. At the web interface for statistics education, WISE, you can do a power calculation for a one sample z-test. It will only do it for a one tail, but it's got a rather nice graph associated with it. To run that software, you need the Java runtime environment installed on your computer, but that's a freebie that you can download. Russ Lenz's PyFace applet has got some nice little tools. You can do a power calculation for a single sample t-test, which you can also use for a paired t-test if you enter the difference between the pairs. And for a two sample unpaired t-test, it will do it assuming equal variances. That software also requires that you have the Java runtime environment installed on your computer. We learnt that testing for agreement is done using the precision of a measurement, which is indicated by its standard error. And agreement of a measurement with a known value is done by calculating the 95% confidence interval, which is twice the standard error on either side of the measurement. And we look to see whether the 95% confidence interval includes the value that we're testing against. If we're looking for agreement between two measurements, then we can calculate the standard error of that difference by squaring the standard error of the first measurement, adding that to the square of the standard error of the second measurement, and taking the square root to get the standard error of the difference. And then we use that to calculate the 95% confidence interval of the difference to see whether that includes zero difference. We looked at tests for comparing a measurement with a known population. If we've got a single measurement and we're comparing against a known population, we use the normal distribution test. If we want to compare a sample with a known population, then if the population standard deviation is known, we use the one sample z-test, and if the population standard deviation is not known, we use the one sample t-test. We also looked at how to compare samples, and to compare the mean of two paired samples, we used the paired t-test, and to compare the means of two unpaired samples, if the population standard deviations are known, we use the two sample z-test, and if the population standard deviations are unknown, we use the unpaired t-test. And that came in two varieties, either using equal variances or unequal variances between the two samples. And if we wanted to compare the means of more than two samples, we saw that we could do multiple t-tests, or more properly, an analysis of variance. So you see, in this lecture we've covered quite a range of different tests for comparing means. What I hope that you can do, if you find the need to compare means, is use this summary to find which test is required, and then you can go back to the part of the lecture that deals with that particular test to remind yourself of how it can be done. So I hope you found at least something in this rather long lecture of use, if not immediately, at some time in the future anyway.